So I'm going to give another example of this theorem and how it's used. So this is the most general version of the theorem that we talked about, where you have a number of rotations and translations, and you can do these rotations and translations in any order. And the result is that after you do all these translations and rotations, that the sum of the angles involved in the rotations can be used to tell you whether F, the product of all these rotations and translations, is a rotation or a translation. If the sum of these angles is not an integer multiple of 2 pi, this will be a rotation about some point C by the sum of these angles. If the sum of the angles is an integer multiple of 2 pi, then F will simply be a translation by some point. The example we want to talk about is from a quiz I gave last spring. And we'll see then how this works. We have a triangle that's more or less random here, ABC, in this picture. And I have some squares. So one square is this BDEC, that's offside BC of the triangle. And another square is this ACGF, which is offside AC of this triangle. And the point P and the point Q are the centers of these squares. So we have P here at the center of this square, and we have a Q that's the center of this square. So Q and B are known at this point, so I look at BQ, and I make another square with that going in this direction, this square that is then going to be the square QBHI. And the problem is to show that the distance from P to I and the distance from P to A have to be the same, and that this angle API has to be a 90-degree angle, a right angle. So that's what we're after. We're going to do this in parts. The first part says to let F be the product of these two rotations. First a rotation around Q by pi halves, and then a rotation around P by pi halves. Remember, these rotations are always counterclockwise, and the problem is to find out what is the value of F of A. So we're rotating around Q by pi halves, followed by a rotation around P by pi halves. And here's A. We want to know what happens to A if we do those two rotations with A. Well, keep in mind that Q is the intersection of the two diagonals of the square. It's the center of the square, and that those two diagonals intersect in right angles. So that means that AQC will be pi halves, will be 90 degrees. So if I rotate around Q, this point A by pi halves, it's going to take A to C because these distances will also be the same. So we're going from A to C when we rotate A about Q by pi halves. So we go from A to C, and now we want to rotate around P by pi halves. So I want to take this C and rotate around P by pi halves. But again, P is the center of the square, and so if I draw on those diagonals here, CPB will be a 90-degree angle, and CP and BP will be the same length, so C is just going to go to B. So A again goes to C with the first rotation, and then from C it goes to B with the second rotation. So the answer to this is F of A equals B. So I put the rotation we were talking about up here, and now the problem is to look at the theorem we were just discussing before we started this problem and notice that this product of rotations has to be a rotation because the sum of the angles is pi halves plus pi halves, which is pi, and pi is not an integer multiple of 2 pi. So it's not 2 pi times some integer. So this is going to be a rotation around some point by pi. And so looking at the question down here, we see that the point x we still have to find, but the angle phi is pi. We're rotating around x, some x, by pi. And now the question is, where is x in this picture? So remember that this f function is taking a to b. So that since this is the same thing as, write it in here, f is equal to a rotation about x by pi, then we know that this rotation takes a to b because f of a was b. So we want to somehow go from a to b by doing a rotation about some point x by pi. So the question is, where would x have to be? X is going to be right here in the middle of AB. And that's because we want the distance from x to a and x to b to be the same because we're rotating around x. And since we're rotating by pi, we want the angle AXB to be pi. And so that's going to put x right here. So let me go ahead and draw that in. That is where x should be then. So that answers the problem here that we had. We found the angle phi. It is pi, and the point x is drawn in the picture. There is one other point y that's in the picture, such that we can calculate what f of y is. That's also in the picture. Okay, so how can we do that? Well, if I look at any of these points, most of these points, when I rotate about x by pi, I'm going over in this area someplace. I'm not going to be in the picture anymore. The only points that where both y and f of y are in the picture, we have a goes to b, b goes to a, and x stays at itself. X doesn't rotate. It's the center of rotation. So I said not to tell me y equals a or x, so that leaves b. Y has to be b. B is going to a, and we can see that in the picture. F of y, we can easily see f of b is equal to a. Okay? So that's the answer to C. We want to take y equal to b. And now we're basically are asked to finish the problem. So we know that f takes b to a, and somehow we want to use that. And what we want to use is that we know f goes from b to a because it's a rotation about x by pi, but we also know what f is in this form. And so f of b has to be a by looking at this as well. So let's see. We want to take b, rotate it about q by pi halves. So we want to rotate counterclockwise around q. Remember, this was a square. Okay, so this length and this length are the same, and this is 90 degrees at q. So b is just going to go to I when I rotate around q by pi halves. So b goes to I. And then we want to rotate around p by pi halves. So we want to rotate around this point by pi halves going counterclockwise. So we want to go in this direction. And what do we know? Well, we know we have to end up at a because, again, f was a rotation around x by pi, and it took b to a. So we know that I has to then go to a. So I has to go to a after a rotation around p by pi halves. Well, if I is going to a under this rotation around p, that makes this distance and this distance the same like we want. So the distance from p to I and the distance from p to a are equal. And it also means this is 90 degrees because we're rotating 90 degrees counterclockwise to go from I to a. That really finishes this problem. We just got to write down that in words. We're getting f maps b to a, and also that it maps b to I and then a by looking at f in this form. And so that last rotation going from I to a is telling me that these two distances are the same, and this is 90 degrees.